Hey everybody, welcome to the last video of transformations. Today we're going to kind of put it all together, looking at multiple types of symmetry, and then a third type of transformation which we haven't really discussed yet, but it's relatively straightforward, called translations. And all the translation is just taking a shape and moving it, right, by either left, right, or up, down, if we're talking about it being on a Cartesian plane, right? So what types of symmetry have we talked about? And so far in the previous videos, we've talked about linear symmetry and rotational symmetry, and even kind of combining both of them, right? So what we're going to talk about in this video is what happens, or how can we identify it when those are happening, right? So for example, here's just 3 different diagrams, and we're being asked to determine the types of symmetry that we see. So if we're looking at this first one here, it can be difficult to tell what type of symmetry we're looking at, right? Depending on what point is associated with what point. So for example, if I look at this shape, A, B, C, D, this rectangle that's up here above my x-axis, right? And I look at this shape, E, F, G, H. You could probably say that there is a relationship between corners A and E, B and F, C and G, and D and H, right? And what that is that's a translation. What that's telling us is that the shape A, B, C, D can be translated down so many units, and when we do that, there's an overlap with shape E, F, G, and H. But that is not the only type of symmetry, right? We could also say that maybe the relationship is not A to E and B to F, but instead A to F and D to G and B to E and C to H. And what that is that's a reflection, right? So if I were to take my line of symmetry, which is actually my x-axis, and take this shape A, B, C, D and reflect it through that line, right? It now ends up down here. And how do I know where the line is? Well, it's all about distance. It's all about distance traveled, right? So if I'm looking at kind of the distance between points B and E, right, to go from a point that's up here at 1 on my y-axis and down here at -1 on my y-axis, it has to go down 2 units. And then the same thing is true to take me from C to H. It goes down 2 units. Or in other words, if I were to kind of put a line that's right in the middle here at 0, it's 1 unit from my line on this side and 1 unit from my line on that side. And then the same thing for B and E, it's 1 unit and 1 unit, right? And the same thing happens for A to F and D to G. From A to my line is 4 units, and from F to my line is also 4 units, right? And then from D to my line is 4 units, and from G to my line is another 4 units. So if you think about it like this, think about it like you are standing in front of a mirror and you are looking at your reflection, right? If I had a measuring stick or a measuring tape and I measured the distance that I was from the mirror, and let's say I was a meter from the mirror, what I would see is that my reflection would be holding the exact same measuring tape on the other side, and it would also be a meter from the mirror. So the same thing is true for these shapes, right? If I can find the position of this line in which that all 4 of these points are the same distance from this line that's all 4 of these points, right? That's where my mirror has to be, and that's how I can tell this is a reflection, right? Now, these 2 shapes have one more type of symmetry, and it's actually a rotational symmetry, right? What there is you can actually take this point B, and we can rotate it to make it overlap with another point down here. And where we would rotate it, or where we would rotate it about, is right here, right? So if I were to take this distance to go from this point to B, right, and take that and rotate it 180 degrees, so now it's pointing downwards, notice that I'm actually end up at point H. And if I were to take the same point and go to C, right, left and up, and rotate that 180 degrees, right, where am I now pointed? I'm pointed towards E, right? And if I were to do the same thing for A and the same thing for B, right, what we would find is that we would have, again, this nice little bit of rotational symmetry that takes all of these points, right, and reflects them, or rotates them, sorry, onto my new points in my image down there, right? So A goes to G, and then finally D would go to F. So what we see is we actually have multiple types of transformations that can actually take my triangle ABCD and turn it into my triangle EFGH, right? And it's kind of up to us to figure out how many types of symmetry, what types of symmetry, and how the symmetry is working, right? So if it is linear symmetry, well, where's the line? If it is rotational symmetry, well, how much am I rotating, and how about where, right? Where is that point at which I am rotating, right? Let's look at the next one. So if we look at this one here, A, B, C, D, E, F, G, H, again, there is a translation that we could talk about. We could say, well, this rectangle here simply just needs to move down one and then over, what's that? Over 1, 2, 3, 4, 5, 6, 7, right? So if we went over 7 and down 1, we would see that we end up kind of exactly overlapping this rectangle right here. Right, so that's one type of transformation I could do to get from my ABCD to EFGH, but we also have a rotation as well, right? If I put a point right here, if I rotate about this point, what I see is that C, right, moving 1 unit, again, rotate 180 degrees, puts me here, right? B, having to go down and over, right, again, rotating 180 degrees, goes over and down, right? A, same thing, so A that was over here, right? Again, if I rotate that, I end up over here, right? And we see that there is rotational symmetry as well, right? For the same reason that there was in the previous example. The problem with this one is there is no linear symmetry. It looks like that maybe there is some kind of line that can take this shape and turn it into that shape. But the thing about like these Cartesian planes, these 90-degree planes, is the only linear symmetry. The only reflections we're really going to find is reflections in the XY axis and the reflections in the up down and reflections in the left right. As soon as I start trying to kind of move on a diagonal, reflections don't really work anymore. So we have to be careful about that, right? So whereas this one can be translated, right? It can be reflected and it can be rotated. Right? This one can't be reflected. It can still be translated, right? And it can still be rotated, right? But there's no reflection that's going to take A, B, C, D and turn it into E, F, G, H. And then finally, if you look at this third example over here, maybe I'll let you guys do this one. So maybe take a break for a second, see if you can't tell me what types of reflections. And if you figure out the type of reflection, then tell me how it gets reflected, or sorry, reflected or rotated. Okay, and then we'll go through it here in a second. Okay, so if we take a look at this shape ABCD, right, A, B, C, D is this triangle that's kind of standing vertically, and then EFGH is a triangle standing horizontally. Okay, for this one, there is no reflection, but there's also no translation either, right? But this one, we do have rotation. Okay, so hopefully we figured that out. So if we do have a rotation, now we're going to figure out how is it being rotated. So we always got to figure out two things when it comes to rotation. We have to figure out what point isn't moving, or what are we rotating about, right? And we have to figure out how much are we rotating. So if we look at these two shapes, there is exactly one spot on both of these rectangles that overlaps, and it's this point right here in the middle. Right, there is an overlap from my rectangle ABCD and EFGH at this kind of point right here in the middle. So I'm rotating about that point, and now we just need to figure out how much we're rotating. So to go from this point to each corner, right, we can kind of think about that, right? Think about the distance traveled from that point that's not moving to every corner or every vertices of my shape, and then that distance is what I'm going to want to try to rotate. So if I rotate it 90 degrees clockwise, what I see is that I get A turning into F, and if I did the same thing for B, it would turn into G, and then C would turn into H, and D would turn into E. But I could also rotate 90 degrees counterclockwise and take A and turn it into H, and take B and turn it into E, and take C, turn it to F, and finally D, turn it to G. So there's more than one option here. It's not that we have to do it exactly that way, but what we see is we have a couple of different options. We can either rotate it 90 degrees clockwise or 90 degrees counterclockwise. All right, let's take a look at another example. So here's another shape, right? So we have our rectangle ABCD, and we're trying to see what would happen, or how would we do these different transformations to it. So again, I'm going to get you guys to pause the video here, try to do these 3 transformations and see what you can get, and when you come back, we'll go through the answers. Okay, so let's start off with rotation or transformation number 1, which is a rotation of 180 degrees about the origin. So the origin, when we talk about this Cartesian plane, is where the x-axis and the y-axis meet. Okay, and it's at the point 0, 0. So again, when I'm trying to rotate about a point, right, I'm always thinking about how do I go from that point to my vertices? How do I rotate these corners of my shape? Because once I have the 4 corners of my rectangle, I can draw my rectangle by simply connecting them, right? So if I want to go from my origin to point D or my origin to point C, I'm simply just counting how far over do I need to go, right? So from origin to D, I have to go over 1 unit, and from my origin to point C, I have to go 1, 2, 3 units. So when I'm looking at rotating the shape, what I can do is I can rotate these distances traveled, right? So if I take a look down here, my original shape has these as its coordinates. Point A is at -1, 1. Point B is at 3, 1. Point C and point D are given there. But then what happens is, if I'm taking this point that was at -1, 1, right? So again, that means I'm going -1 or 1 unit to the left on my x-axis, right? And 1 unit up on my right, on my y-axis, and I want to rotate that 180 degrees, it's going to take those directions and it's going to do the opposite. It's going to take that movement of left and make it go right, and it's going to take that movement up and make it go down. So if we do that, right, we go to the right once and we go down once, we see that we have this image point A here, right? We do the same thing for B, C, and D. Now something interesting happens here. Because my Cartesian plane is broken up into 4 quadrants, right, where each quadrant is separated by 90 degrees. When I look to rotate by a 90-degree angle, 90 degrees, 90 degrees, 90 degrees, the number value on these points actually only just change signs, right? So that movement of 180 degrees, or that rotation of 180 degrees, takes my -1 and turns it positive, and takes my +1 and turns it negative. Takes my 3, 1 and turns it into -3, -1, right? Because we are simply just rotating it 180 degrees, which means instead of going in the positive x direction and the positive y direction, we would be going in the negative x and y direction. So nice little trick there. If I want to rotate 100 degrees, all I really have to do is take the 4 points of my original shape and change their signs. Okay, part B now, reflecting about the x-axis. So again, we have to understand what that means. Well, the x-axis is the horizontal axis, right? It's this line right here, right? So again, that's my mirror. So we can think about this in 2 ways. A reflection can be thought of as a rotation, and it can be thought of as another reflection, which is kind of a weird way to think about it, right? Because why wouldn't I just reflect it? Well, again, the idea here is, well, how do these coordinates or how do these points match up, right? So what does reflecting something about the x-axis do? What it does is it takes everything that's above my x-axis and it simply moves it or places it reflection exactly the same spot but below my x-axis, right? So where this point A is up here at +1, right? It's at -1 on my x-axis, but it's at +1 on my y-axis. By reflecting it through my x-axis, it's actually going to put it down here at -1. So it's going to only change the sign of these y values. This +1, +1, 0, and 0 are going to become -1, -1, 0, and 0. Now, what happens if I want to think about it a different way? Well, again, we know what happens when we rotate 180 degrees. What that does is it changes all my signs. It would take this -1 and make it positive, and take this +1 and make it negative. But the problem is we don't want our x values. We don't want these numbers to change signs, because that's what happens when we reflect. So then what we have to do is we have to reflect it about the line in the middle here. We have this nice little line, this vertical line going down the middle of my shape that I could then reflect it to turn the signs back to what we wanted them to be, right? So there is different ways of doing this or of thinking about this, but generally speaking, because we are talking about doing something on an XY axis, right, we can really see what and how these things are going to happen. Okay. Finally, part C says to translate it 4 units right and then 1 unit down. So again, what we can do is we can simply just perform that to each of our 4 points. We can take point A, point B, point D, and point C and their coordinates, and we can actually just add or subtract depending on what I am doing. So 4 units to the right. Right and left are talking about the x coordinate of my point. Up and down talk about the y coordinate of my point, right? Right means it is positive. Left means it is a negative movement. And then for the y's, up means it's a positive movement and down means it's a negative movement. So if I want to translate 4 units to the right and 1 unit down, all I have to do to my coordinates here are add 4 to all of my x values. So -1 plus 4 is 3. 3 plus 4 is 7, 3 plus 4 is 7, and -1 plus 4 is 3. And I can subtract 1 from my y values. 1 minus 1 is 0, 1 minus 1 is 0, 0 minus 1 is -1, and finally 0 minus 1 is -1. Right? But we also see that there is this nice little symmetry happening by doing that. Because we have moved it in this way, what we see is that we actually get a shape that also has rotational symmetry. So there is always this nice little overlap between what types of transformations not always, sorry. There is sometimes these nice little overlaps between translating and rotating and reflecting and rotating. So we have to be aware of these things and we have to see that there is a relationship there. So if you ever ask a question like this in the future, right, when we're trying to identify and describe the types of symmetry we get when we have these resultant shapes, right, we have to be looking for these different types of symmetry and speaking to them. Okay, so I'll leave this question for you to do. Again, maybe pause the video and very, very quickly at the end, once you're done, I'll go through the solutions. Okay, so here is my shape ABCD. And again, what we're trying to do is we are trying to perform the following transformations, right? So again, to start, what we really want to look at is where are these 5 points, right? So points A, B, C, and D. And E, sorry, have the following coordinates, and then the same thing is true down here. So now if I'm trying to translate these points, it is simply just a matter of taking these values and adding or subtracting them to my original values. So if I want to move down 2 units, that's going to take my y coordinate from each of these points and it's going to subtract 2. And if I want to move left 3 units, it's going to take the x coordinate of each of these points and it's going to subtract 3. So simply, all I need to do now is take these numbers and perform those operations. So 6, 5, 5, 7, 7, we're going to minus 3 from each of them and we get 3, 2, 2, 4, 4. And then 8, 7, 4, 4, 7, we're going to minus 2 from each of those and we get 6, 5, 2, 2, 5. So when I do that, when I put in my new points here, I will find these 5 new points for my shape. So we go over 3 up to the 6, and then 2, 5, 2, 2, 4, 2, and finally 4, 5. Take these points and we'll connect them, and we'll have our new shape A, B, C, D, and E. And there's my A prime, my B prime, my C prime, my D prime, and my E prime. Okay, and then finally, if I want to do the same thing for my my reflection here, right? Reflect the pentagon through 5 on the x-axis. So what does that mean, 5 on the x-axis? What it means is it means find the number 5 on the x-axis. So the horizontal line here is my x-axis, and the number 5 is right there. So what that's telling me to do is it's telling me to take a line at 5 and make that my mirror, make that my reflection, right? So now, how do I reflect these points? Well, what we're going to do is we're going to find their distance from 5 and then go the same distance in the other direction. So for example, points B and C, they're right on 5, right? So we don't have to worry about moving those. They're going to stay at 5, okay? Point A, on the other hand, is 1 unit more than 5, so its reflection is going to be 1 unit less than 5. Okay. Point D is 2 units more than 5, so its reflection is going to be 2 units less than 5. And then point E, again, same thing. Because we're only reflecting a line that's going through my x-axis, meaning we're only moving it left, right, there actually is no change to the y values of these coordinates, so they'll stay at 8, 7, 4, 4, and finally 7. So now if I plot these new points, right, here they are right here. Maybe let's pick a different color so we can see our new points. So there's my new A, my new B, my new C, and then my D and my E will stay on the same positions because they're right on my line. So there's my new A, B, to C, to D. There we go. All right, so here's my new A prime, my new E prime, and my new D prime. I will use double primes again to indicate that these are not the same shapes as the one before. Okay, so that is it for transformations, and I will see you in the next one.